Well, good morning, everyone. How are we doing today? The rain is done, the sun is shining. People are excited to be here. Can see all those big smiles. Welcome to EECS 151, lecture 22. Today, we're going to really be getting into the fun stuff. We're going to start talking about sequential logic. But before we do that, we need to finish up last time talking about Booth encoding and how to design efficient multipliers. So please go ahead and give this warm-up a try. Go ahead and take a few minutes to solve this on your own. All right, so let's talk about this one. So recall from last Thursday's rainy lecture that Booth encoding is a trick that we play in partial product generation when we want to multiply two binary numbers. And the trick is, instead of looking at a single bit of B at a time, we look at 2 bits of B to decide what partial products to generate, right? So the 2 bits of B are here in the table, B sub k and B sub k plus 1. And then also we have a sort of extra kicker bit coming from the previous set of bits. which is this b sub k minus 1. And we did some cleverness with how those are arranged so that we're only ever adding or subtracting 0 or a or 2a. Right, so in particular, these last 4 rows are minus 2a, but then it's really plus 4a. So that adds another bit to the next column of generation that we look at. This is really minus a plus 4a. And same with these last two. And it's whether this extra plus 4a is here is what sets our b sub k minus 1 for the next column. So the trick with Booth encoding is simply to figure out which row of this table we're in and then fill in the partial products appropriately. So we ran out of time a little bit last time. Can folks tell me a quick Vista 5 how you're feeling about Booth encoding and about this problem? Okay, yeah, a lot of 2s and 3s. So let's spend a little more time on this and make sure we're kind of squared away. So let's go through this example, right? Remember, our goal is to look at 2 bits of B at a time, so that you'll notice that instead of how many bits of B are there in total? Well, there's 7. So if we did a sort of normal multiplication, we had 7 different partial products to generate. But here we're just going to wind up with 4. So that's the benefit. The benefit is obvious right away. We have half as many partial products. The complexity is that the generation of those partial products is no longer just an AND of 2 bits. So let's take a look. Start with the first 2 bits of B, which are 1, 1. For the very first set of bits, there's no b sub k minus 1. There's nothing to the right. So it's going to be this row of the table, right? B sub k and b sub k plus 1 are 1, 1. And then the minus 1 is 0. So that's how we get minus a in that first row. And so we just copy a down and write a negative sign to indicate that it's negative. So any questions about what was already given to you? Now, the key to remember is that in this row, this minus a is really minus a plus 4a. And so we'll make a note to ourselves, the b sub k minus 1 of the next row is going to be 1, right? Because adding 4a for this precision, if you shift over by 2 bits, that's the same as adding a for this next group of 2 that we're going to look at next. Okay, so let's tackle the next one. We have 0, 1, and then we have b sub k minus 1 equals 1. So what should go in the box on the right? Anybody? Yeah. Yeah, plus 2a. You don't have to write the plus. I'm just writing it to be as explicit as possible about where we are. Yeah, so exactly. We're here in the table. Right. You can think of, if you want, you can think of this b sub k and b sub k minus 1 as having the same weight. And then the b sub k plus 1 has twice the weight because it's 1 column over. Okay, so we know that, and I'll put the zeros in explicitly just to make sure we're aligned on place. We're shifted over 2 already. And then because we're doing a plus 2a, we need to shift over 1 more. And then we can copy in our a bits, 1, 1, 1, 0, 1, 0, 1. And that one's positive. And did that result in a extra plus 4a for the next set of bits to look at? It didn't. All right, this is just plus 2. So now we come to the next 2 bits. Well, this should be pretty easy to deal with. What do we write here? Yeah, it's just 0. So I'm not going to spell it out, but it's all zeros. Now, we do still occasionally get zero partial products when we Booth encode. Right? It's like a 1 out of 4 chance instead of 1 out of 2 chance. Okay, so then once again, we have no +4 coming from the previous group. So our b sub k minus 1 is 0 for this last row. So it's just a 1, which is sort of implicitly a 0, 1. And so what should go in this last box? Let's hear from someone else. Yeah. Plus A, exactly. And so we need to line it up with our partial product, right? So we're 6 places over. And then we'll copy A, 1, 1, 1, 0, 1, 0, 1. Yeah, you can these b sub k minus 1 operations, they feel sort of like a carry. They're not a carry, right? We're not doing addition yet. We're just generating the partial products. But it's the same idea as a carry, where once you get enough significance in the current column that you're looking at, you add something to the next column, the next set of bits. Okay, and then we're not going to do it here because I'm confident that you all can do it, but the final step would be to sum the partial products to get the result. Yes? This one, yeah. Yeah, so why did I shift 3 instead of 2 here? Can someone explain that? Yeah. Yeah, so 2A, so we shift 2 because of the place that we're in this set of 2 bits, right? And then if we're adding 2A, that's equivalent of A shifted left by 1 place. That's why 2s and 4s are very nice when we're doing binary operations, because as we've seen in this exercise, multiplication is expensive, right? If we wanted to do 3A, that would be expensive. That would be complicated. But if we want to do 2A, you just 4A, we're done. So, and as an aside, if there are places in, say, your processor design where you're multiplying by, a fixed amount, and that fixed amount happens to be a power of 2, you can just do a shift instead, right? You can skip this whole exercise of having to design a multiplier in the first place. So that this is a very common trick, is to try and do shifts instead of multiplies because it's so much cheaper. Oops. Okay, sorry. Skipped ahead there. Okay, any other questions about this example of how to do Booth encoding? Yeah, one more in the back. Yeah, so in practice, you can either you can represent this as 2's complement, and then just do the addition. We're not going to. Yeah, there's multiple ways that you can implement the partial product summation when you have to deal with negative numbers. We're not going to talk about that more in lecture, but yeah, just keep in mind that it's one little nugget of complexity that you have to handle with Booth encoding. It turns out to be not that expensive, is the TLDR, to handle adding up the negative partial products. Okay, so this is Booth encoding in a nutshell. As we said, the key advantage is that it reduces the number of partial products. So our Wallace tree depth for the carry save addition becomes, instead of log of base 3 halves of n, becomes log base of 3 halves of n over 2. Right, we have half as many rows in the limit. But as we just talked about, partial product generation itself becomes more complicated. Okay, we haven't, and we're not going to in lecture, going to go through the details of the logic, the Boolean equations that you would need to actually generate the partial products. stay tuned for a possible homework question where you may have to think about this more, but I'm confident that you all, as we're nearing the end of this class, are fully capable of figuring that out. So Booth recoding or Booth encoding, typically used for larger multipliers. I would say 16 bits or 32 bits or larger is where you tend to see Booth encoding used more. As always, the trade-offs depend on the details of the design decisions, of the process, of the standard cell implementation, and so forth. And as noted here, and I'll just mention very briefly, occasionally we don't need to just multiply two numbers. We need to multiply many numbers or multiply numbers repeatedly over and over again in, for example, a FIR filter, if you're familiar with signal processing. And so there are some additional clever twists on Booth encoding that you can employ in those cases. We're not going to talk about that more. Yeah. Yes, good, very good question. So radix 8 Booth encoding would be looking at 3 bits at a time instead of 2. You can do it. People have done it. The number, you can't just get away with A and 2A anymore. So you do need to now generate 3A in order to make that work, that hard multiple. And the number of partial products has just gone down from n over 2 to n over 3, right? If you're looking at 3 bits at a time. So it's kind of like past radix 4, the costs kind of go up like this and the benefits go up much more slowly. So I would say in practice, radix 8 would be possible, but rare that would be optimal. And then past radix 8, it's almost certainly not going to make sense. That's a very good question, though. Yeah, in theory, there's no reason you couldn't design a multiplier like that. For large multipliers, yeah, I would say radix 4 often ends up being the best design for performance. Okay, so hopefully that example and discussion is helping folks feel a little more confident about Booth recoding, which wraps up our discussion of multipliers. We are going to move on in a moment. If you're still feeling fuzzy on this was also discussed in detail in the discussion sections last week, so I'd encourage you to go watch the recording of that. There's a good explanation, again, of how this works. Before we wrap up, I do want to talk briefly about the sort of practitioner's view of arithmetic circuits, okay? So in practice, and as you've already been doing in your final projects, right, most of the time you need to lay down a multiplier. You're just going to assign with the multiplication sign, right? You all have already done this, almost certainly. This is what most digital designers will do most of the time for multiplication or addition, or any number of other arithmetic operations that you might be interested in. In a lot of cases, that's enough. So the synthesis tools will use this to generate a multiplier. And in particular, they're calling under the hood, when they see a multiplication sign like this, they look at the number of bits, and then they look at this pre-built library of components. Synopsys calls theirs designware. Cadence calls theirs chipware. So that's what you're seeing in ASIC Lab. FPGAs have their own set of pre-baked components. And they're just basically doing a very simple lookup function. You know, how many bits is it? Are we asking for a fast one, or does it not need to be that fast? And then they have a table, and they say, okay, well, let's go implement a prefix look ahead adder because this one needs to be fast. And they put in those gates and then they synthesize it. One second. So that's what you will do in practice most of the time, and that tends to be good enough. I think a lot of early digital designers assume that these arithmetic circuits from the vendors must be like totally optimized and there's nothing else to do there. That's definitely not the case. These are pretty good trying to cover everyone's use cases. But if you have a really critical block, like say a tensor core in a GPU, you're not using design work components, right? There are going to be design experts that are using everything we talked about in these lectures and much more advanced concepts in arithmetic circuit design to go in and hand design exactly what gates you want and exactly what microarchitecture you want. And you can see gains of 20 to 50% in performance or power or area, depending on the details of exactly what you're looking at. So the utility of these lectures on arithmetic circuits is not necessarily that every time you need an adder, you're going to go in and do this detailed analysis every time, but it's really useful. Like, occasionally, you will need to do that, and it's important to have those skills. And then it's also just really useful to have intuition about what's going on behind the scenes, right? If you think about, oh, I want to go from, say, RV32 to RV64, my adders are going to go from 32-bit to 64-bit. How much more expensive is that? Well, we know from delay, from if you're using a fast prefix adder, you're only adding one more stage, right? Because it scales with the log base 2 event. So having that intuition about how these things scale and how they're designed is super useful, even if you're not most of the time going to be doing the design yourself. Okay, there's one question, I think.
If I choose a block based on whether it's timing, but how does it know? Is that like part of the same timing optimization? I think.
Yeah. So a lot of synthesis and a lot of all these tools are iterative passes. So there will be an early pass where it does a very rough estimate of what it thinks the timing is going to be through all the different blocks, and then it'll make a guess about, okay, I think we need this kind of adder, and then it'll iterate on that. Yeah, there's a lot more details that I'm eliding, but at a high level, that's what it's doing. Okay, so let's wrap up multipliers. We talked about binary multiplication, right? Same technique fundamentally as what you learn in elementary school, just with bits instead of base 10. We saw that multiplying is actually very easy. It's just an AND gate for 2 bits, but that summing the partial products is the hard part. And so you can build this simple version that's just a parallel array adder, but it's going to be quite slow. You can use carry save adders, which are a special kind of adder that's very useful for adding multiple numbers together to add up those partial products. And you can optimize it further into a tree structure called a Wallace tree. And then finally, we talked about Booth encoding as a way to reduce the number of partial products. So that's our whirlwind tour of multipliers. Okay, any last questions before we move on to today's topic? Okay, cool. Let's move on then, because this is now where the fun begins, the real fun. Okay, we're moving. Combinational circuits are in the rearview mirror now. We're going to start talking about sequential logic, which we've talked about before, but we haven't really, in a more detailed sense, explained how it works, how to analyze it, what's really going on under the hood. So today, I think we're probably not actually going to get to flip-flops. We're going to talk about timing, and then we're going to start talking about latches. And then on Thursday, we'll talk about flip-flops. Briefly, here's our abstraction hierarchy. You've seen this slide many times now. Perhaps you're sick of it. Too bad. Timing lives up here. And so for the first part of this lecture, we can mostly understand timing analysis just by at the sort of RTL, register transfer logic level, right? Where we have some state elements and then a blob of combinational logic and then some more state elements. When we want to talk about latches and flip-flops, we actually need to get down more into transistor level design to understand exactly how those are working, what makes them tick. So this is sequential logic. You've seen it all before. That's all right. We have one or more state elements, right? And in particular, we have a flop here, R1. In the context of timing analysis, we would typically call this the launch flop or launching flop. So on the clock edge, it's going to launch some data that's going to propagate through the combinational logic. And then it's going to get captured by the capture flop. It's going to be received by the capture flop before the next clock edge, right? So that's fundamentally the high level understanding of sequential logic. But let's get into the details, right? Because they're unlike combinational circuits where if you give it enough time, it'll always eventually get the right answer if you design it correctly. And sequential logic can go wrong if you don't get the timing correct. So we need to do some careful analysis about how to get the timing correct. Now, this is our flip-flop. This is how you instantiate it in Verilog. You all know this. The flip-flop has 3 key timing parameters that, along with the cycle time t, we use to analyze its performance and the performance of the whole circuit. Okay, you can see them marked on the diagram here. We're going to define those now. Okay, just to be crystal clear, right? The clock pin is what triggers the flip-flop to pass data from D to Q. If we're not at the rising edge of the clock, then the flop is going to retain its previous value and send that to the output Q. So that's the behavior functionality. We're all familiar with this. Let's look at how we analyze the timing. So there are sort of, as I mentioned, 3 key parameters. The first is the setup time. It's labeled as TSU, T setup, on the diagram. And I'm going to write the definition first, and then we'll look at how it shows up on the diagram. So the setup time is the amount of time before a clock edge. That the D input must be stable. Or to say it another way, D needs to be totally set up, hence the name, some certain time before the clock edge triggers, right? The whole rule with flops is you never want their inputs changing at or near the clock edge, because that way lies disaster. That way lies functional failures. And so you can see in the timing diagram, D transitions right at the edge of the setup time. This is the last legal time that D is allowed to transition. During this setup time here, D must be stable and unchanging. So this is a property of the flop. It's a requirement for the signal going into the flop to adhere to this in order for the flop to work correctly. Okay, now let's talk about hold time. Hold time is sort of the mirror image of setup time, if you like. So it's the amount of time after a clock edge that D must be stable. Again, you can see it annotated on the diagram here. You'll notice that D stays stable for some time after the clock edge. That's the hold time. And then it transitions. But that transition is not reflected in Q, which means that the hold time the hold time constraint has been satisfied. So this is the flip side of no toggles in D near the clock edge. Right? Once the clock is fired, you still need to hold D constant. You need to leave it alone for a certain amount of time before you're allowed to start changing it again. Okay, and then finally we have the clock to Q delay. Clock to Q delay is a little less scary. It's not a constraint imposed on the rest of the design. It's just a property of the flip-flop itself. So clock to Q delay is the delay from the rising clock edge to the output Q being updated. So if we look at, once again, what's going on in this timing diagram, but now thinking of it in terms of these three terms that we just defined, right? So you notice that D toggles Q, D and Q start both low. D toggles high right at the edge of the setup time, which is legal. And that means at the clock edge, D is going to update to Q, right? But that doesn't happen until the clock to Q delay. This T clock to Q here. So you'll notice that after that delay, Q updates. In the meantime, after that hold constraint, after the clock edge, D toggles again. But we're not near the clock edge, so that means Q is not going to update until the next clock edge, right? When there's another clock to Q delay for Q to go low following D going low. Okay, so these are the three key parameters that we need to analyze the flip-flop and analyze the timing of the circuit. So based on these parameters, let's go ahead and look at the two fundamental timing constraints that we need to analyze or solve for in order to guarantee that our sequential logic is going to function correctly. The first is the setup time. This is probably the one that you're more familiar with. This is probably the one that you've spent time staring at or analyzing or even optimizing in your labs and final project. A setup time is the constraint where the first flip-flop, the launching flip-flop, launches the data on the clock edge, and the second one captures it on the next clock edge. And so you need to make sure that the data arrives to that second flip-flop before the next clock edge. We need to look at every single path in the design in order to analyze the setup time and take the very worst case. So this cartoon only shows a single path, but there will be thousands or even millions of paths in your design. I'm not going to show that explicitly in notation, but just keep that in mind. So the minimum cycle time is T is set by the longest path. And so the setup time constraint is that the cycle time must be greater than or equal to, let's follow the progression of the signal as it goes through from the first clock edge to the second. Well, the clock edge fires, and then sometime later, the output will come out of that first flop, out of Q. And we just define that time as T clock to Q, right? Then the signal propagates through the logic. And then we have our final constraint, which is that that signal needs to arrive sometime before the second clock edge. We just defined that constraint as T setup. So this is our setup time or cycle time constraint. And then we'll also introduce the concept of slack. It's probably not an introduction. This is, again, something you've very likely seen in your timing reports in your labs. So slack is just whatever's left over from this inequality. Okay, so we can rewrite this inequality as the setup time minus everything on the right side. Yes. That's right. Yeah, it's not explicitly written here, but T is the clock period. Yes. Yeah. So in both ASIC or FPGA are doing a version of this, and when it generates your synthesis reports, there will be some sort of timing report that you can look at. And it'll list some timing paths, and then it'll say at the bottom of each path, it'll say slack, and it'll either say met or violated in big letters, right? And so in particular, If a slack is met, that means there's positive slack, there's extra. If slack is violated, that means the slack is negative, and that means you're not meeting this constraint. Yeah, good question. So for setup, as we alluded to earlier, it's not just doing one pass to optimize the design, it's doing iterative loops, right? So if it's on loop number 1 and it finds some paths that are violating the setup time constraint, it'll go back and optimize those paths and try to make them faster. If it's on loop number 25 and it's still stuck, eventually it will give up and just report out to you. All right, we're gonna talk a little in a few minutes about what to do if we're failing, I guess, but that's roughly what the tool would do. Okay, any other questions about setup time constraint? And this one is obviously very important, but in some ways it's less scary than the one we're about to look at. Okay, I'm not going to explain exactly what I mean, but hopefully you'll come to understand that as we go through it. So the second fundamental constraint that you need to satisfy in your design is called hold time. Hold time, unlike settle time, hold time is a little trickier to wrap your head around, I think. So let me try to explain it in words and then through the equations. Unlike setup time, which was looking at one clock edge and then the next clock edge and defining a constraint between them, hold time is defining a constraint for the same clock edge. So it's saying the clock arrives to launch flop R1, and then let's imagine that there's a very fast path through the combinational logic, and it arrives at this D pin even before that same clock has arrived at R2. Another way of saying this is that the launching flip-flop should not contaminate its own data that it has already stored in that second flop for the subsequent cycle. And this is sometimes called a race condition because the data is racing through to update that flop when it shouldn't. Okay, let me write down the constraint, and then we'll talk about it a little more. So the hold time constraint, T hold, which we defined on the previous slide, the time where D needs to be stable after the clock edge arrives to a given flop, must be less than the clock to Q delay, right? So that's that clock propagating through the launch flop, plus the minimum delay through the logic. And we haven't really talked that much about this idea of minimum delay, right? In all of our studies of combinational optimization, logical effort, arithmetic circuits, we've always been focused on the worst case delay, the slowest possible path through a circuit. So the slow path is what you care about when you're analyzing setup time on the previous slide. But for hold time, we actually care about the sort of best case or fastest possible path through a circuit. The best case and worst case timing can vary quite a bit. And so I've written that as the minimum delay, the minimum path through the combinational logic here. So this is our hold constraint. Hold slack, once again, is just the difference when you subtract this inequality. So we could, again, define it as the difference of the two sides. So T clock to Q plus T logic min minus T hold. Or again, positive slack means that this term in parenthesis is larger than the hold time, and so you've met the constraint. Negative slack means you've failed the constraint. So one of the reasons that hold time seems a little non-intuitive is that it seems like this should be trivial or easy constraint to satisfy, right? In particular, if the clock is arriving at both of the flops at the same time, how can there somehow be a path that's so fast that D can update before that clock edge? Right? It seems almost paradoxical. And so indeed, in many cases, hold time is not an issue. But when it is an issue, it causes big problems, right? It means that the flop is going to be updating when it's not supposed to be, and it causes a functional failure. Make one other observation here. There's one parameter we don't see in the hold constraint. There's no cycle time in this constraint, right? So hold is independent of cycle time. It doesn't matter what you set your clock period to. It doesn't matter how frequently the clock toggles, because it's a constraint from the same clock edge for both the launch and the capture flop. Okay, any initial questions on hold time? We're going to look at some examples, and I think that will probably provoke some more questions. So this slide helps to visualize the different arrival times that we talked about and the different slacks. So here's our clock, right? Here's clock for cycle 1. Here's clock for cycle 2. We'll look at each of the constraints in turn. The hold time is saying the data must be stable for a certain period after the clock edge. And only then is the input to that flop allowed to start toggling. The setup time, again, is saying the opposite. The data must be stable before the next clock edge. And so we have this late required arrival time, right? That's the last time that data is allowed to transition. In this kind of golden period or green period, I guess, based on the diagram, you're allowed to switch as many times as you want. So D can toggle arbitrarily as long as it doesn't switch before the start and it does switch before the end. And then finally, we show on this diagram where the slack arrives. So if the actual first time that the signal starts switching is here, then we had some slack, some early slack, right? We had a buffer between the requirement and the actual time. So this green arrow is the hold slack or the early slack. Similarly, on the other end, if the worst case combinational delay winds up here, then we have this late slack on the right side. That's saying that we had extra buffer time before we had to finish the combinational logic. So this diagram kind of nicely summarizes all of the concepts that we just talked about. I'm going to try to present it one more way on this slide to sort of tease out these two different constraints. So again, the setup constraint is that data transitions on the launch flop must settle before the next clock edge arrives at the capture flop. Whereas the hold constraint is that data transitions from the launch flop have to not propagate too soon to the capture flop on the same clock edge so that it doesn't contaminate its own data. So when are these problematic? Well, the setup constraint is violated if combinational logic is too slow. I think that's where you get setup time failures. It means you haven't arrived at the subsequent flop in time. The hold constraint is the opposite. The hold constraint is violated if the combinational logic between the two flops is too fast. There's not enough delay between the two flops. And so the data from the first is contaminating the data from the second before it's ready. So what I'd like folks to do now is turn to a partner and discuss how to fill in these remaining 4 boxes in the table. In particular, think about what to do if your combinational logic is too slow for the left column and what to do if your combinational logic is too fast in the right column. So let's go ahead and take 4 minutes, discuss this, and try to fill in the 4 boxes with your partner now.
Is that intake or after? Whatever. I mean, like we get good spray. I know, right? You get a nice feedback after that. Yeah, bringing it up. And we noticed that if it's oh yeah, I mean it's just not. Oh, but hey, I don't know. I wait, that's yeah, it's the same as not using your levels. Like what between the yeah. But also you can't yeah. We can always I don't know especially just like
All right, let's come back together. I'm hearing some interesting ideas. Oops. Let's try that. Okay, let's come back together. Thoughts. Who would like to fill in one of the boxes? Yes. Which box are we filling in? Yeah, so one option is to decrease or yeah, decrease F, I guess, increase T. Okay. Yes. Oh yeah. Yeah, and that's the common way to fix fold. If your path is too fast, the most common case is just when it's a flop and then another flop with nothing between them. And so you can just add buffers to slow it down. Other thoughts? So what do you do if your chip comes back and you taped it out at 500 megahertz, but at 500 megahertz it's not working? Right. You're going to have very likely you have some programmable clock generator either on the bench apparatus or on your chip, right? So you can always turn down the frequency and make the chip work. Right? Not so secret is that production silicon that is in your phones and computers is doing this all the time. Right? Companies will sign off at a very aggressive target, 3.2 gigahertz or something, and then they'll ship at 3 gigahertz because it didn't quite work. It sucks, but you can still get the chip out the door. There are of course other ways. Can anyone think of other ways to fix the setup constraint at design time besides just backing off your frequency target? If you have a combinational path that's too slow, what else can you do? Yeah. Sure, yeah. You can repipeline.
You can try to optimize the combination.
Yes, you can optimize the Boolean logic to have fewer gates or fewer stages. We're going to talk about that in a minute, so I'm not going to write it here. But yes, you can use clock skew to help with this. You can always play, you can also play with gate sizing, right? Like we did in the logical effort lectures. Um, any ideas for how to fix hold after tape out? If you have a hold problem after you've taped out your chip, you're in big trouble.
Can you not increase your clock speed?
Does does hold does the hold constraint depend on the clock period?
No.
So it's possible that you can try to play tricks with voltage. Yeah, some hold violations only show up at certain voltages, and so you can just avoid operating there. One clever trick that fortunately I've never had to do, but I've heard of people doing, is you can play with temperature. We haven't talked about this, but it turns out that transistor performance is temperature dependent. So in some cases, if your chip is sitting on your bench not working and you spray it with the freeze spray, it will start working. Not very practical, but at least you can demonstrate that it may be a hold problem. You can do very expensive things like what's called a FIB, or a focused ion beam, where you take your chip to a lab and they actually poke into it with a light source and cut a wire or draw a new wire. Expensive, can't do it at scale. No, hold after tape out is really bad, right? So this is, if you have one takeaway from this lecture, it's that setup is important because it sets your performance, it sets your frequency, but you can always address setup issues by backing off frequency after tape out, right? Hold is super scary and very difficult to deal with without retaping out a whole new chip. Yeah.
Stuff like
Yeah, we're going to talk about exactly when you might want to fix these, but yeah, during physical design in particular is when you fix a lot of hold issues. So even though this hold constraint seems basic or trivial, right? You just need to make sure that there's like a buffer or two between every flop. In practice, hold is a big headache because you really, really need to be very, very sure that you got it right. And so you tend to add a lot of margin, or you make sure that there's some hold slack in every path. You don't tighten it exactly in order to guarantee that. Okay, one more question. Yeah, you could think about I guess repipelining could help with this as well. Right? If you had an imbalanced pipe stage where you're doing a lot of work and then very little work, you could rebalance it so that both pipe stages are doing some work. But the most common fix is to just add buffers. Okay. Let's take a brief pause and talk about how the rest of the class is going. Okay, I think folks are I hope, well into your final projects by now. Those checkpoint 2 checkoffs are continuing to roll in, so please do plug away at that if you haven't yet. You're now pretty deep in the experience of being an actual digital designer with all of the pain and suffering that entails and getting a working design out the door. This is the real experience. I want to talk briefly about checkpoint 4, which was announced on Friday. So checkpoint 4, it's sort of not a quote unquote real checkpoint. You won't have a checkoff for checkpoint 4 by itself. We'll just have one big checkoff at the end of your whole final project. But the purpose of checkpoint 4, apart from running through place around and so forth, is optimization. Right. So we've provided these figures of merit, which are somewhat complicated looking equations, but they're basically just saying make it faster in as little area as possible. So checkpoint 4 says optimize your designs as much as possible. And then of course we have this design contest sponsored by Apple, where we're going to take the top N designs based on this metric. And there will be some prizes at the end. as folks probably know. We have set up a leaderboard on Gradescope where you can upload your snapshot of your design files, and it will show you how you're doing in terms of your figure of merit. So that should give you some guidance if you do decide to participate. Okay, not everyone's going to participate in the design contest, and that's totally fine, right? This is just if you want to go the extra mile and try to really show that you can optimize your processor through clever techniques, microarchitecture or architecture techniques. Any questions about checkpoint 4 or the final project? I know it's a few weeks down the road still, so maybe it's not quite on people's radar yet. Yeah. Correct. Yeah. Yeah. You'll upload the formats are specified in the checkpoint 4 documentation, so read that carefully. But basically, you upload the synthesis logs, and then it will parse it and figure out how you're doing. And just to be clear, we will go and verify the top end designs that you haven't just gone in and edited the logs and uploaded that. So please don't do that. Yeah, but it's intended to give you a snapshot and see how you're doing in the design contest. Okay, cool. Let's move on. Let's look at an example of timing analysis. So this is a sort of cartoonized version of the actual critical path in Intel's Itanium 2 processor, which was, I think, about 25 years ago now. And so we're just being asked to analyze the setup slack of this design, calculate the setup slack of this design if the clock period is 1 nanosecond. So for the setup time analysis, we need to find the longest critical path through the design. In this case, the longest path is pretty obvious, right? It starts at this flop, it goes through the adder, goes through a mux, a wire, a mux, a wire, a mux, and then back to that same flop. Interestingly, we have the same flop here as the launch and capture flop. That's fine. It doesn't change the analysis at all. We're given a bunch of delay parameters on the left that we can use for the calculation, right? So first, let's figure out that slowest logic delay. So we went through an adder. And then we went through 3 muxes. And then 2 wires. So that's the delay through the combinational logic in this path. If we add those all up, 600 picoseconds plus 3 times 80 is 240. So that's 840 plus 200 here. So this is 1040 picoseconds. And then we can use that combinational delay to calculate our setup slack, which recall is not just the combinational delay, but also depends on the flip-flop parameters. So we're comparing our clock period to the clock to Q delay plus that logic delay that we just calculated, plus the setup time, because we need to meet the setup time constraint. We were told our clock period is 1 nanosecond, which is 1,000 picoseconds. And we have clock to Q of 20, logic max delay 1040, and a setup time of 50. So the result is negative 110 picoseconds of setup slack. So is this design meeting timing? No, it is not. We're 110 picoseconds shy. So we need to either back off the clock period or repipeline or optimize the logic, right? Any questions on this example? Yeah. Yeah, so once again, clock to queue is just the time between when the clock arrives to the launch flop and the output actually propagates to the queue. So you can think of it as the delay of the flop when it's launching the data. Yes. Oh, good question. Yeah. Can anyone think of a reason why a MUX might have a faster or a slower delay through the MUX? I'll give one example, a sort of generic example. Right? Think about our when we were analyzing the delay of CMOS gates, and we said anytime we have transistors in parallel, we need to size them for the worst case when only one of those transistors is on and driving. That's the slow case, right? But we also have a fast case where both of those parallel transistors are on and driving. And so you could see in that case, you would have, depending on exactly how your inputs are toggling, you might have a slow delay through that gate, or you might have a faster delay. Yeah. Um, for a combinational gate, the difference tends to be not that large. For a like multi-bit circuit, like an adder, for example, the min versus max delay can be quite large, as is shown in this example. Because for our adder, we were always looking at what's the slowest delay to that last bit, bit 31, typically, to calculate the very last one, right? And that set our worst case delay. But data could start to change much more quickly in bit 0. So you have this case where the fast bits, quote unquote, of the adder can be toggling way, way, way before the slowest delay through the adder. Yeah, as I said earlier, we haven't talked a ton about this sort of min delay or fast delay concepts, but really every gate or logical structure you can think of as having a fastest possible path or a slowest possible path through. Okay, so I'd like you all to try this next part on your own. Same circuit, just go ahead and analyze the hold slack instead of the setup slack. And go ahead and take 3 minutes to do this on your own. Look at the second bullet point there. Oh, yeah, yeah. Sorry. I'll leave this up for one more minute and then we're going to vote on the results. Okay, can I turn on the voting screen or people need more time on this? All right. All right, let's take one more minute. Please go ahead and vote if you haven't already. All right. I shut off the responses. Let's go ahead and talk about this one. It looks like most folks have responded at this point. So what is the fast path through this design? Uh-oh. Any thoughts? Yeah, so the very fastest path is going to be here, right? Right. Notice this bullet point. So assume all mux inputs not drawn come from another flop. So implicitly, there's another launch flop here. So it's definitely not safe to assume that the fast path is going to be the same one as the slow path, right? Because remember, these constraints need to be satisfied for the entire design. So there was a little bit of a trick, but not that much. Um, so given that, we can analyze the hold slack, right? So we need to account for the clock to Q delay of this hypothetical launch flop here. And then the min logic delay. And we need to see if that exceeds the hold constraint. So this should work out to 20 plus 50, the min delay through the mux, minus the hold constraint of 40. So this 30 picoseconds. So does this design meet the hold constraint? Yes. Hold slack is positive, thank goodness. Yeah.
Is that the point that generally we want to be really sure that the constraint matches? I mean, like, beats the constraint?
Yeah.
Is it normally that you want a constant amount of hold slack or some percentage?
Very, very good question. It's not always going to be a constant amount. In particular, it will vary based on the voltage target or the frequency target. So you could think of it as some percentage of your clock period. In the research or academic designs that I have taped out, where we don't care that much about performance and want to be very conservative and have higher odds that it works, I usually target a slack of like 100 picoseconds, something on that order, just to make sure there's lots and lots of extra margin. In a production design, you're going to be a little more picky, right? Because it's not cost free. Adding these buffers can get pretty expensive if you want to add lots of slack everywhere. So in industrial designs, they'll do much more careful analysis to figure out exactly how much they think they need to add, and then still probably add some fudge factor on top of that, but it wouldn't be 100 picoseconds, it'd be less. Okay, let's move on. In the last few minutes here, I want to talk a little bit about clock non-idealities, and then we'll wrap up for today. So one of the assumptions implicit in every lecture so far is that we have this magical clock source that can magically perfectly arrive at every flop at the exact same time. Of course, a moment's thought will convince yourself that that is not in fact true, right? So clock arrival, in fact, varies in space and time between when it actually gets to these different flops in your design. Some of the sources of uncertainty are labeled on this slide. I'm not going to get to step through them all, and there are more not listed here. But just know that there are a bunch of different factors in the messy electrical real world that will cause your clocks to not perfectly arrive at every flop at the exact same time. And so in particular, I want to define two terms. Clock skew is the spatial variation in temporally equivalent clock edges. And there's both deterministic and random components. And in particular, a positive skew between a launching and capturing flop is that the receiving clock, the capture flop, is receiving a later clock than the launching flop. And a negative skew is the reverse. The negative skew is the captured clock is arriving earlier than the launching clock. So you can see the skew demarcated here in the diagram. Jitter is related concept, but different concept than skew. Jitter is a temporal variation. So it's saying in each cycle, that clock edge is not going to arrive exactly 1 nanosecond after the previous one. There's going to be some cycle-to-cycle variation based on how good your clock generator is and other factors about when it arrives. And so we have this jitter factor, which is saying each clock edge does not arrive exactly when it's supposed to. So we demarcate that TJ. And so, in fact, we need to go ahead and update our timing constraints to account for the presence of skew and jitter, right? And so that minimum cycle time, we now need to subtract the skew and add jitter. The jitter is always hurting us, right? Because we always need to add extra margin to account for the fact that the clock edge might arrive in, exactly the direction we don't want it to. It might arrive late, or it might arrive early for the capture flop, for example, or late for the launch flop. Skew, per the question earlier, can actually benefit us, right? So in particular, you'll notice that positive skew makes it easier to meet this constraint if the clock edge can arrive later to the capture flop. Okay, and then for the hold constraint, we similarly need to update so now we'll say T hold plus T skew plus T jitter needs to be less than our minimum delay path. Unsurprisingly, the impact of skew is the opposite for hold, right? So in this case, negative skew or early arrival of the clock at the capture flop can help us meet that constraint. So it leads to this sort of interesting trade-off where, yeah, you can deliberately skew the clock and it's going to help one of your constraints and hurt the other one. There's no free lunch here, but we do need to account for it when we're performing this analysis with non-ideal clocks. So in practice, in solving problems for this class, you can assume that these skew and jitter terms are 0 unless we specify otherwise in the problem, because a lot of first order analysis, you just don't consider these terms. But if you want to really get the details right, you do need to account for clock skew and clock jitter. Okay, any questions on non-ideal clocks? Yes. Sure, sorry. All right. Oh, one more question?
Are skew and jitter something that sort of just test for or you calculate?
You can do analysis of skew and jitter pre-tape out in the same way that you analyze other timing paths in your design. Yeah, we won't talk in detail about how you would do that. I think for now, just know that they do impact your timing calculations. Okay, so we're at time. We've just about wrapped up our timing analysis segment. So on Thursday, we're going to get into the details of how we design latches and flip-flops.